and the Raman modes and other things. So my job is like a bit easy. So I'm also new and our institute also new, like it's like 10 years old. And you might heard first time Triple IIT Vadodara. And one of the good things, like we have two campus. Now it's going to be three. So one is in the Gandhinagar now, and second we are building in the Vadodara. And third, we have a beautiful campus, international campus, we say in Diu. And Diu is very famous for like beautiful beaches, and this we Google it just Ghogla Blue Beach, so you can go and enjoy. And also it's like known as the Europe and India. It was like a Portuguese colony, so still like they followed all the European culture. And I came directly from Italy to Triple IT Vadodara due in December, so it's like 6 months. So it's not much challenge because it was like kind of Europe. So thank you. So I'm going to talk about the why we need this graphene, fluorographene heterostructure, and what is the advantage of this to use in the optoelectronic devices and other things. So, and still like we are in the conference where lots of 2D materials we are discussing. So why the 2D materials play the important role? So if you see in our lab still we have a silicon based detectors if you want to measure the photoluminescence and other things, and it's very nicely it works up to the I think 1100 or 1050, and when you need like some materials which has a infrared like the emission or something, so then you need to now change these detectors, and they are very expensive, and also you need a low temperature and other things. So one of the key things that graphene was discovered, and it has a very fascinating property, right? Mobility, carrier density, and the other key thing was the optical absorption. So if you see this is one of materials which has the broadband absorption from the UV to terahertz. There is no other material which has this kind of absorption. So this is the key thing. So what happens like if you have this graphene and make this light sensing device, to take the piece of graphene, put the electrode, and then simply shine the light, and then you see very poor photo response, right? And then you calculate the responsivity milliampere per watt, and the silicon ampere per watt. So then again we came to find the competitor of silicon and other things, but still very poor performance. So what is the advantage? So the main reason was like carrier recombination. So when we have the graphene, when you shine the light, carrier will like create electron hole, but it's recombined in such a way in picosecond or femtosecond, even though applying the voltage you cannot separate, but simply you can integrate with the silicon very nicely. Now you will see graphene and silicon, very nice photocurrent you can see. So one thing, integration is possible, right? But this discovery somehow give a new opportunity to explore the all other 2D materials which are like Professor like Sony discussed about other TMDs and thing. So same thing like long back in 10 years ago, I think more than 10 years ago, this Andraskis group, they came with this let's exfoliate the monolayer MOS2 and see the photo response behavior, how it looks like. And this is the monolayer MOS2, this is how they make the devices. And if you see they have a nice response like similar like the silicon, but only they can go up to 680 nanometer. So if you have a 700 nanometer light, it cannot absorb. So then again it's a problem, right? Silicon 1000 something. So then we also try to check whether it's true or not. So then we have this monolayer MOS2 and CVD. Also we check with the exfoliation, very nice single layer. And when we shine the 700 nanometer light, there is no response. That's true because it's not absorbing here. And if you have 633 or 533, we can see clearly a very nice photo response. Similarly with WS2, we want to check, verify it's true or not. So monolayer WS2 devices, again at 700, there is no response due to their absorption. Basically they don't absorb above the 680 or 710 light. Okay, so this is one thing, but you can integrate this MOS2, WS2 with different low dimensional materials where they can act as a photo absorber, and then you can make 2D, 0D and other kind of heterostructure. Okay, right? Now now we found like some of this very interesting material. CRSBR is a Janus structure, chromium sulfur bromide. And what you see the interesting thing, if you have like the room temperature, they have the emit the infrared like 90 nanometer PL, and when we go to the lower temperature, the PL is split. So this is like kind of fancy, like they have the magnetic ordering and some different physics like behind. And what good thing, like now I can go up to 850 nanometer. So these materials can absorb up to 850, or I have the laser up to 850, so I just try to 850, and we have now very nice response. And the other key thing, this kind of material, they have very nice in plane anistropy, like Ashish was discussing yesterday. So also when you change the polarization, you can change the device performance. So now we have the multi-control parameter, like you change the temperature. This is typically behave like a semiconductor. So change temperature, change the voltage, change the excitation energy. So you have the multi-control. Also change the magnetic field. You can put in the magnetic field, you have the different photo response. So multi-controlled photo detection you can do in this kind of material. And also another is CrCl3. Professor Singh is here, like he can have a large scale CrCl3 like materials. So also we try to see whether this CrCl3 show similar kind of behavior or not. So this is in the progress, like we might have some in the later. So 2D magnetic semiconductor. So now I'm happy, at least I can have 850 nanometer. But can we go beyond 850, like 1000 or mid infrared? So still I stick with graphene, like maybe some people critique why you still using graphene, doesn't have a band gap and this thing. But it's very easy to now make the devices and integrate, right? For example, if a quantum dot. And why I'm saying we don't need the fancy technique like lithography, EBL, simply like just put the silver paste and put in the graphene and make the contact. The wire, you can simply see the very nice IV characteristic. If you go to micro level, use the TM grid like the G200, and then even though a 0.5 centimeter graphene, you have a 200 devices. So there is no need like the fancy lithography, and it's very easy to do it in the lab also, right? And then you can simply integrate with this quantum dot, like for example, graphene quantum dot, EU, GQD, also the converted nanoparticles, and then you have the different structure, right? So this is one of the good thing, and I'm not criticizing the TMD's family. Also, it's like TMD also working very nicely. And then also recently we combined with this 3D perovskite with graphene, and we have very nice circular polarized light detection. Okay, and then also you can have the Persian blue magazine nano composite on graphene. So several kind of like you have the graphene as a template, bring your low dimensional material which can absorb the light, and they can transfer to the graphene. The graphene act as a carrier transport and charge transport materials. And then we have the very nice photocurrent. You see in this case like very high, like in the milliampere range, which is like still like one of the highest in this kind of system what we absorb. One good thing about graphene, now Graphena, a Spanish company, they have a 20 centimeter large graphene. 20 centimeter. TMD is impossible. Still we not, processing has 4 centimeter, but 20 centimeter you cannot reach. So one good thing, now silicon has 40 centimeter, but more or less like we can reach up to scaling on this one. And I take around 10 years to like get a very nice, beautiful, interface in graphene when you transfer. There is no polymer and other things. So very high quality graphene. Also, you can put this like silver glue to make devices. Also, we can transfer this graphene on different substrates like the quartz, and then we can measure the very nice broadband absorption. I want to verify also it's true or not. See, you can very nice photo like absorption. So one problem with graphene was the carrier recombination, right? Due to the CBD, yeah, it's a graphene company, right.
How you transfer it?
Simply, I will explain this, just finish and then, yeah, okay. So, one thing with graphene is a carrier recombination, right? So, can we like break this symmetry and try to, get rid with this recombination? And can it possible? So, then we found, okay, yeah, this can possible. And also, we want to get rid of sp2. I don't want sp2. If you want to open the band gap and remove the symmetry, we have to go to somehow sp3. Then you have the optical band gap is changed, and then you have now some kind of like gap. Okay, and these guys, so graphene, the good thing, they have the decolized pi electrons, lots of pi electrons, right? And they love the electrons. They will easily go and take the graphene, the electrons from graphene. And if you see the electronegativity here, fluorine is very high. So they love more, okay? So we try to, okay, let's functionalize this with the different functionalization group. So chlorine, fluorine, hydrogenation. So all we tried, and we see fluorine works nicely because it has very high electronegativity, and it will go and make carbon fluorine bond. Okay, so this is the thing. You can also try hydrogenation, but it's very hard to break the symmetry. Still, like so the metallic behavior of this one. Okay, so when we came with the fluorographene, that time like 6 years ago, so then we find lots of one good thing we know. Okay, when we have this xenon difluoride exposure of the graphene, it's very easy to make the fluorographene. And when you have the fluorographene, also you can easily control the degree of fluorination by changing the time of the exposure of this one. And then these are the open question out there, like stability, how this is stable. Also, when you do this fluorinated graphene, you lose the mobility and also the optical absorption and lots of things. And then these two reports, as Professor Soni was also discussing some of the contradiction, right? So both guys came each other within a week, and one they say, okay, when you do the fluorination in the monolayer graphene using this technique, you have the only single side fluorination, top. This nanometer, they saying no, it's not true. When you have this same graphene on silicon silica, both the substrate is same, you have both side fluorination, top and also the bottom. So it was like, like more or less, then I came into the picture, okay, let's check, this is the good opportunity to know, okay, whether it's true or not, right? Okay, and other thing like, okay, when you have this graphene and fluorographene heterostructure, basically you can double the mobility in the literature. Also there are many literature, and their answer was common. Okay, when you have this fluorographene on the bottom, it's system like HBN graphene, so there is no substrate interaction. Also the dangling bond issue will be resolved, and then you have high mobility as they have mentioned. Okay, but nobody telling okay what happened in the Raman and whether they have any interaction in graphene and fluorographene or not. It's very easy to say, act as a substrate like HBN. Okay, then we came with this idea. So this was not my idea. Okay, this my boss, he worked lots of thing in this kind of constellation with the MIT in the Metal Dressel House. So he say, okay, one thing we can do, we have isotopes level graphene. So only carbon 2 isotopes is stable, carbon 12 and 13, and 13 in the worldwide only we have 2 group, one in the MIT and also now my boss had this isotope. So he said, okay, one thing we can do, let's make this kind of system where do the fluorination in the bottom, one graphene, and then put another layer on the top in such a way, so you have 3 regions, one is the fluorinated, one is the heterostructure, and one is the pristine, and then probe layer by layer, because when you have the same isotope, same Raman spectra position, you will not take a risk to say, okay, this layer is doing this and this layer is doing this. So this was one of the key things. Okay, so then we came with this idea. So how we prepared our sample? So this is our sample preparation. So we have now carbon 12 isotopes graphene on the silicon silica. Then we expose in the xenon difluoride. Now we have very nicely fluorinated graphene. We break the symmetry, and then we transfer the another layer on that one to check our heterostructure. Okay, and we use both. So it's for CBD we have the isotope. For the bulk graphite, you will not have the carbon 13 isotope. Still, we don't exist. Okay. So interestingly thing. Okay. So let's go one by one. Then you will understand more. So this is our pristine monolayer graphene with the carbon 12 isotope. You can see there is no D mode. Okay. Then we expose in the fluorination. Now very nicely this D mode came. D mode is also indicator of sp3 hybridization. Okay. And then also you have the D prime, G, and the 2D. So it's basically, it's now defective graphene. We created the defect in this one. This is the carbon 13 graphene isotope. So they have the, of course, mass is change, different vibration, different Raman mode. But here also we can say there is no D mode in the, so it's basically pristine monolayer graphene. Heterostructure. Interestingly, if you see, now this is going down, this is going up, this is going up. So basically, you have now minimum defect. So what's happening in this one? That means the top layer graphene is coming to the bottom and then taking some of the fluorine or atom from the bottom layer. Because when we do the fluorination, they are not strongly bond with the bottom layer graphene. Some of the loosely, they love electrons, right? So when they come like similar like lollipop, like okay. So they love and they go. So that's why now the D mode decreases, and then you have very nicely this G and 2D mode increase. So this is with the CBD sample. We further try to prove exfoliated and CBD. Okay. So we have the bottom with the CBD, and then we put exfoliated. We have the similar result, like the 2D increases and also this D mode decreases. So what's happening? And then it's the Raman mapping to further confirm in the large scale. Okay, it's not a point data, is true or not. Then also we came, okay, let's check high quality sample with the exfoliated. Okay, then now you have exfoliated sample, high quality, and the same manner. So all the control, heterostructure, everything you have together. Then we perform the Raman mapping. Again, we see the same result. At this region, this is the fluorinated, we have high ID by IG. Here is pristine, and this is here less. So basically, you are passivating the defect, right? And then we perform the KPFM. We got a similar result. At the heterostructure, we have the minimum CPD and the maximum at the pristine. So from this, we came in the observation. So basically, the top and bottom layer both are interacting. Okay, and the interaction is electrostatics, we say. Okay, and then also, because when we don't have this, fluorine is not stable. So when you don't have any top layer, so fluorine will migrate, right? So basically it also somehow prevent the electron drain from the bottom layer. And this is a kind of synergetic effect. And also we observe shift in the G mode, which also indicator of the charge transfer. So this is happening here. Okay, very nice. So passivation and this thing. So one referee asked, okay, what happens if you have a HBN? HBN is a perfect insulator. Then we say, okay, let's do again one experiment. Then we came with this one, fluorographene and with the HBN. So here we have this fluorographene the bottom, and then HBN thickness was like around, I think, 6 to 7 nanometer. What we see, there is no change in D mode. So the ID by IG value was same. Somehow it prevent the fluorine. Fluorine is still there. It acts like a capping layer, but there is no interaction. That's one clear indication. The top layer basically taking the sum of the fluorine atom, and it's a kind of like a sharing thing, which we further confirm from the XPS where we observed a shifting in the binding energy, which also indicate this is the now sharing of this bond length on this CF bond length, and a clear evidence came from our Sims spectra where what we see when you have the only floated graphene, you see there is no kind of like aging issue, also it is not uniform. But when we have this heterostructure, very nice charge cloud, that top layer came and both they stabilize the fluorine atom. So this is one of our observation, and we say clearly this is interaction. There is no only act as a substrate, it has the interaction. Okay. Then third thing, why we cannot make the devices? So same structure, same materials, everything, just I put the electrode like this, and then we measure the IV characteristics. Interestingly, you see, so this is your monolayer, okay? This is a monolayer graphene with the 12 isotopes. When you fluorinate, defective, drain current decreases a lot, right? But when you have heterostructure, now again this guy came and you have very high, nice drain current, right? And then we see the photo response, very nice. And if you see the only graphene, so much noise, right? So now we see the for the 4, 5, 7, 4, 8, 8 now very nicely photo response. You can see, and also the responsivity 10 to the power 4 order. It's very high. It was a milliampere, now we can reach 10 to the power 4. Another thing is the stability. Why silicon is still in our lab? Stability. We make the 2D materials, you can say, and you ask me, can you produce tomorrow the same result? I will say no. Sorry, honest answer. Very hard, very hard. So reproducibility and also the stability is the key issue. That's why still silicon is there. And I asked this question to Professor Anandam Ghosh when I was in Cambridge, and he gave me the honest answer. Silicon will only finish until silicon is not exist. So silicon will be there. Okay. So I'm not saying to change this one. Okay, but we have a nice photo response. So another is stability. So let's check whether this device is stable or not. So I measure around 1 year the sample every 3 months. Okay, take the sample again, the same parameter, same condition, everything, and very nicely we can see up to 86% the device was retention was the same. So 86 to 89% is highly stable. Another question was fluorine. Does fluorine is still there or not? And how to confirm? Do the XPS, very easy. Also Raman, but XPS is the more elemental things. Okay. So if you see day 1, we have very nice fluorine in the fluorinated single layer graphene. After 1 year, this fluorine is gone. But when you have a heterostructure, day 1 and day this one, after 1 year, still fluorine is there. So basically, this top layer, when we have a heterostructure, it's also prevent the fluorine migration. So they have the interaction, which are like kind of like, they don't allow to go there. Okay. Another thing, we also check the stability of this sample by Raman spectroscopy also. When we heat, up to what temperature this fluorine can bind with this top layer of graphene. Okay. And then here is our photo response with the temperature. And what we observe, up to 200 degrees Celsius, this device was quite stable. Why? Due to this top layer, because it provides some kind of capping, and also it's holding the fluorine, and that's what we need, right? So it's working. Then we have one colleague who do the very nice MD simulation. Then I asked him, can you do a bit for like this kind of system and how it behave? So he came with the lots of simulation he have done, and this paper is there. So we try to see by the videography how it's working. So now this is a monolayer fluorinated graphene. We try to increase the time and also the temperature now increasing, and you can see now it's fluorine start to now going from this fluorinated graphene surface. Okay, so it's not more or less stable. So and there is no protection, right? So fluorine can go anywhere, right? But in the bilayer system, if you come, so see, we are not allowing the fluorine to go from this graphene surface. So now they will go and maybe probably go to attach on the top. So see, so basically fluorine is not going anywhere. So still we have on this heterostructure. So the puzzle was this, okay? And so what was the problem about this? So he said, okay, when you have monolayer fluorinated graphene, okay, this is the graphene without defect. So when you heat this one at 300 or 400, this guy will decrease because fluorine is going. When fluorine will go, D band will decrease, and this G and 2D mode will increase. So he was saying like this, but this is saying no, it's not true. So basically when you heat, one side fluorine will go and still second side is still there, and that's why see clearly this D and G mode. So they are fighting. So and what we observed, this was not true in our case. So all the samples CVD, very high quality fluorination, okay, very high degree of fluorination in all the cases, and our was the in situ Raman, We increase and better control than the annealing the sample in the furnace. And what we observe, when we increase the temperature, this IDY is decreasing, and you see clearly this D mode is decreasing. But here they say it's not. This is a CVD sample. Then when we say, okay, maybe sample has some artifact, we came with the exfoliated high quality sample. The same result, similarly. And he was a reviewer of our paper. So multiple time always he had just only, why your data is not matching with our one. He clearly reveals in the many and 2-3 journals, he was the main reviewer. Okay, so I was like, get angry. And the main, what they try to say, because your silicon oxide surface is not uniform. So it kind of have like, wrinkles or something. So when you expose the fluorine is going from the bottom and also coming from the top. So basically, you have double side fluorination, which was not true in our case. Then I was very much angry. So then I was see, okay, let's see any role of the surface roughness on this fluorination. And then whatever substrate we found in our lab, like glass, quartz, silicon, whatever we have, we just, okay, let's transfer the graphene, check the roughness and do this fluorination. This is how our setup, our look like. Same condition, everything. And let's check whether this is true or not. Any role of roughness? No. They say surface roughness. And we have now different roughness. So here is our result. Now silicon, quartz, glass, silicon nitride, very nice monolayer graphene, and then we fluorinate. So you can see D and G mode is clearly arising. It indicate we have very nice fluorination. Same sample, same time, same parameter, everything. We didn't change the control, anything. Then that time I also use a bit like, I use my IQ. Let's also see some of the suspended sample. Okay, so I transfer the graphene on. You can also do in the TM grid, but we have the silicon nitride, this one with the gold from the, I think, some Canadian company we purchased. This is monolayer graphene, no D, right, high quality. Then we do the fluorination. And clearly, very strong G, 2G mode is there. Okay. Then we again perform the in situ Raman by our system in the helium and hydrogen atmosphere. All these samples, same behavior. When you increase the temperature, your fluorine is migrating and D is basically decreasing. But only in this sample, still this D and G were after annealing 400 degrees Celsius, we could see it's the same behavior. There is no migration of fluorine. That's indicating when we have the suspended, so both sides open, so fluorine will expose on the top and also the bottom. When you anneal, so probably one side will go, one side will still stay. So this is our observation. Then again we came with some different engineering, like, okay, so we have this graphene substrate and then we put one polymer and then try to see, okay, if the is coming from the substrate or going from the bottom, we should see the D mode here also, the fluorinated. But what we see, so we measure the Raman here, clearly we have this D mode, that means the fluorination. But when we the graphene here, there is no D mode. That means fluorine is basically not going through the substrate, only the exposed. Then we also perform the mapping and we could see, like clearly we see only in this area we have this fluorination, this area is clear, it's nothing. Okay, so basically we have only fluorinated graphene when you expose the sample, not is going from, so there is no role of substrate, roughness and other things. And then we also perform this MD simulation. So Javier also found that when we have this bilayer system, like the suspended sample, so both side fluorine, it's very highly stable. That's why we are saying after 400 degrees Celsius, still the fluorinated graphene is stable in the suspended. So this is what like we are trying to have done it in past, and I'm very happy to inform you. Okay, I will go to the next slide. So now we also, so in the xenon difluoride, in the gas phase fluorination, basically you have the limitation of the sample. You cannot have the very high vacuum chamber or something. So we developed a technique in Italy. So now we can have this large area, the vapor scale, 4 scale, fluorinated this kind of system. And also we have this on the fused silica and the silicon silica, you can do in the arbitrary. And then we also came with this idea, can we integrate this kind of system with this low dimensional like plasmonic materials to get the infrared kind of heavy metal free infrared detector something. And this idea was liked by the European Commission, and they gave me this Marie Curie, which I just completed, and like not completed, I just resigned, I have to come back to join. And one interesting thing, this is the first time we can resolve this kind of, what is the carrier dynamics we have in graphene fluorographene system. And you can see still in the femtosecond. Still is our creating defect, even though it's the femto and pico and other things. So this almost, and this study done in Milan University of, I think, Politecnico di Milano. So they have very nice system. They can resolve this pump probe. Okay, so now I joined. After that, I proposed to the director this idea. Okay, can we start one center for 2D materials here? And our main purpose is to train the BTech student and also the PhD and other things, so they can get the idea how to make the devices and materials. And we are in the Gujarat. Gujarat is very famous for semiconductor, so a student can get trained and they can go also the work on semiconductor industry and other things. So this was our idea, and let's see how it works. And now I'm also looking for so many collaborators. And also thanks to our the previous and also still they are here. So okay, so thanks a lot. Yeah, thanks a lot. Now I'm happy to take the question. Yeah. I'm on time. Yeah, thank you. Thank you.
Thanks. You have shown a lot of data in a short time. I think we can take up the questions.
Yes.
Any questions?
The first thing I wanted to know, how do you transfer?
Yeah. So classically people use PMMA. So first code the PMMA and then take the FECL3. Okay, and then you remove. But in PMMA, like I observed, like you cannot remove the PMMA completely.
Yeah, there are particles.
Yes, there. So then we came with a nitrocellulose. Nitrocellulose is very nice. Okay, so you can use nitrocellulose, and no need to heat this nitrocellulose. You have to, for the PMMA, you have to 60 degrees, 70 degrees. Use nitrocellulose. Simply use methanol. Clear, nice interface.
How when you look at the SEM image, how zoomed in do you go?
No, so basically I don't do SEM. I do the optical microscopy. 100x.
You cannot confirm whether the
No,
cellulose is gone entirely. So the
yes.
thing is that graphene has this property of making nanoparticles on its surface.
I mean, some point of view maybe you can correct, but for our observation, it suggests we have a nice clean interface because nitrocellulose. PMMA, this thing happened. So that we have a paper also. You can check, and also we have yes.
Any question from students on the back side? Comments, remarks? If not, let us thanks once again.
Thank you.